also obvious. So what's momentum? As I said, momentum, conservation of momentum, laws of conservation of momentum is used in many areas of technology. So it's very crucial, very important. What's momentum after all? So momentum is a vector for an object which has some mass. If the object also moving with some velocity v, we define the momentum of that object to be its mass multiplied by its velocity vector. So momentum is a vector after all. Okay, momentum is a vector. Momentum of a solid object which has some mass m, and at some point if it's also its velocity, it is just multiplication of mass with its velocity, and this is called momentum. Okay, and over here on this lecture, on this course, we only define the momentum of massive particles, massive objects. Okay, momentum is also defined for objects which do not have some mass, like light. Okay, light rays, photons. Photons have zero mass, rest mass. They don't have mass, but also they don't have mass, they have momentum. So this course is not about, does not cover these subjects. So we only cover the momentum for objects which has masses, and it is defined this way. So why the momentum is important? Why do we need such a physical quantity? We know the velocity, but why do we need extra physical quantity to define extra quantity like such that? Why do we need that? Because there is an associated law with the momentum of any system. So what is that? What is that associated law? That law is conservation law, the conservation of momentum law. Okay. If your system, what the system is, what a particular object is. A system may consist of more than one particles. As I solved many problems about this, and I defined some problems. You have two masses, and let's see these two masses as one system, etc. I solved many problems about this. You might have a system, and your system might consist of many objects, mass 1, mass 2, etc. For example, in this example is we can define our mass to be system of these two students together with their carts, trolleys, and this is your system. If you have a system and the system only interacts your system particles only if your system particles interacts with themselves, and if there is no any external interaction. Okay, well, of course there are external forces on these students, and first of all there are weights which is downward, and there is also normal forces acting on each student in the upward direction, but these forces are just cancel each other. Normal force and their weights cancel each other, so net force is zero. There is no external force in that sense, right? There is no external force on the girl, and there is no external force on the boy. There are forces, normal forces and their weights, but they just cancel each other because they don't move up and down directions. They only move left and right. So if there is no any net force acting on your system, but your system only interacts with themselves, what I mean by is that your system objects are applying some forces on each other, right? In that case, whatever this interaction, or however this interaction takes place, or how long is this interaction takes place, doesn't matter. There is one associated quantity which is attributed to your system, which is the total momentum. And the boy have its own momentum. Let's call this P boy, and the girl in this picture, in this example, have its own momentum. Okay, and their interaction. Well, during their interaction, of course, individual momentums of boy and the girl may change, and as what you see over here, right? For example, initially they are just not moving, they have zero momentum, but when they interact with each other, they move, so they have some momentum. Even their momentum is changing during the course of interaction, during, they're pushing each other, during their pushing each other, their velocity change, individual velocities are changing, right? And their momentums are changing. But one thing I should say, that just before the start and right at the end, in all of these frames in your video, there is one physical quantity associated with your system, such that I can say about this quantity will never change at all. Okay? As I said, the boy has its own momentum, the girl has its own momentum, and they have initially zero momentum, but during all these frames in the video, they interact with each other, they change their velocities, right? And obviously their momentums will change. But I say that some of their momentums, boy and girl, even they are changing, their sum is going to be zero. I claim this, okay? And this is very important for this experiment. The motion only stops at some point over here, but if we let the motion go forever, if this playground, if the stage, if the scene is continue forever in both directions, I can say that this sum will always be equal to zero for all time, till the end of universe, as long as this scene is not changing. Okay? So this is why we define the momentum, because the momentum for isolated systems, what I mean by isolated system, this boy and girl consist of an isolated system, they comprise an isolated system. Isolated system means on boy and girl, on the total system, there is no external force. There is no external force, or all the sum of external forces add up to zero. This is what I mean by isolated system. For all isolated system, whatever the momentum of the systems at one point in time, it is going to be changed. It's not going to be changed at all other times. Okay. So this is one very important and unique thing about the conservation law of momentum, is that the momentum is conserved for all times. The momentum is conserved for all times for isolated systems. So one thing is important over here is that you should always know what an isolated system means. Okay? You know what it means by isolated system. Isolated system, you choose the parts of your system, and you know what your system is. You know what the individual parts of the system. And just look at all the individual parts of the system. If there is other external forces other than the system's interaction, if there is all forces on your system, external system, add up to zero, that means external forces on your system, if it's zero, then I claim this, that the system's total momentum will always be conserved. Okay? It will always be zero. It will always be conserved. It doesn't need to be zero all the time. It is zero for this particular system. But if you take at any time that the momentum is not zero, but some fixed quantity, this momentum is going to be the same for all other times, as long as you have an isolated system. So this is conservation of momentum, okay? Conservation of momentum. And I choose just to emphasize this point by choosing a specific example. Okay, so then let's do this. I mean, this conservation of momentum can give you a lot of precious information on the future evolution of your system, or on some physical properties of system. As I said, as I asked previously about this particular experiment, that I asked you, I said that the only mass of the girl is given, but by just observing this motion and using some parameters in the problem, you will be able to determine the mass of the boy. The mass of the boy is not given here. Only the mass of the girl and the mass of these cards are given. And by just observing the motion of these two students pushing each other, after push, just comparing their velocities, and we will see that comparing their momentums, you will be able to determine the mass of the boy. And this is one precious thing, one very nice thing about this conservation of momentum. Of course, you will not only be able to determine the unknown masses, etc. You will be determining many things, many valuable physical information by applying the conservation of momentum laws. Okay, so let's do this. Let's do this. Let me erase this part again, because I have only this part as my background. So let's go back to the initial frame, the very first frame of your video. And in the very first frame of your video, as I said, your system is composed of the girl on the left, the boy on the right, and the card that the girl is slide on, and the card that belongs to boy. These both cards and the boy and girl consist of your system. Okay. But the thing is, the girl moves with the card, with her on her card, and the boy moves with her on his card. So you can just think that the card and the boy and the card and the girl are together, moves together, unique, stick together. Okay, and let me also write down. Are you able to? No. Read this? No. Okay, this is black. So I will try to give the masses. The boy and the girl and the card mass all together give you this quantity. Okay. I think it's at the end of. So the girl and then the card consists of 57.8 plus 22. It's going to be 79, right? 79.8 kilograms. So the girl side has the mass of 79.8, but this is not the girl mass. It's girl plus her card, and M2. Let's specify M2 to be the boy and the boy's card mass altogether, and it is unknown. Well, we know that the card has a mass of 22, but since we don't know the mass of boy, we can put this as unknown, because we are going to try to figure out what the mass of the boy is. So, since these two objects, the girl and its card and the boy and its card, are moving together, okay, we just name the girl and its card mass as M1 and the boy and its card mass as M2. And we don't know what the M2 is, but we know what M1 is. M1 is 79.8 kilograms. Okay? So, again, if you come back to the very first initial frame of the video, your system at this frame initially has zero momentum, right? And let's put over here the girl momentum and the boy's momentum is 0. Okay, and I take the girl's momentum to be the mass of M1 multiplied by V, and the boy's momentum V1. The boy's momentum as mass of boy together with his card multiplied by the velocity of or speed of the boy. So That means their initial velocities are zero. If the momentums are zero, obviously, since their masses are not zero, v1 and v2 are zero. So initial v1 and v2 are zero. And what's next? What's next is if you run the video again till this point, okay, as they are detaching from themselves, now they are moving with constant velocities because they are not touching anymore to each other. That means there are no other forces acting on the boy and the girl. So if there is no any acting force on the boy and the girl, whatever their velocities over here, the velocities will stay constant. But right after this point, I can just calculate the boy's velocity, right? Because it goes a distance of 20 centimeters in, let's start from frame 0. It goes this distance in how many frames? It goes this distance in 41 frames. On the other hand, the girl goes the same distance in 37 frames. So at this point, their momentums, of course, individual momentums are not zero. Okay, their individual momentums are not zero, and let's denote these momentums as primes, pg prime and pb prime. Obviously, pg prime is just mass of the girl m1 together with its car multiplied by v1 prime, but the v1 prime is the girl's velocity toward left because girl is moving toward left. Let me just put an arrow on the girl in this direction and put v1 prime. Okay, I hope you are able to see this vector because it's black. The background is black, but there is some light anyway. And for the boy, let's put its velocity toward right as v2 prime. So pb prime is going to be m2 times v2 prime. Okay. But you have to be careful that since the momentums are vectors, these directions of the velocities will make a difference. For example, if you take rightward direction to be positive x direction, v1 prime is going to be negative, right? v2 prime is going to be positive. So since the momentums are vectors, then and this is a momentum in one direction only. The system has the momentum in only x. There is no momentum in the y direction. So we give the direction information as the signature of their velocity components. v1 prime is going to be negative and v2 prime is going to be positive. All right. So what did I say before that? If you look at the system's momentum will be zero all the time because the initial momentum of your system, which is pg plus pb, is zero. Oops, let's put this over here. pg plus pb is zero. Then pg prime plus pb prime must be zero, because what I say is that system's momentum, this is some of the momentum of individual parts, is going to be the total momentum of your system. If it is zero, it's going to be zero all the time. Okay, it's going to be zero all the time. So by using this information, let's try to find what v2 prime is. Sorry, what m2 is, because we will be able to determine v1 prime and v2 prime. So how can you find v1 prime first of all? Well, as I said, the girl, after detaching herself from the boy, the girl takes this 20 centimeters in 37 frame. And that means the distance that the girl takes is d, which is 20 centimeters. And the timing for the girl is, let's call this is d1, okay, and this is t1. T1 is just 37 divided by 240 seconds. That's the duration, because one frame just lasts for 1 over 240 seconds, because 240 frames just last for 1 second, and from that you are able to find the duration of 37 frames. 37 frames second correspondence is just 37 divided by 240. And for boy, the distance is the same also, is 20 centimeters, but for boy T2 is 41 divided by 240 seconds. The boy takes the same distance longer time. Okay, so from these two informations, from four informations, you will be able to find what V1 prime is. Let me erase this part. V1 prime is going to be, the magnitude of V1 prime is going to be just D1 divided by T1, right? 20 centimeters divided by 37 divided by 240, and V2 prime is going to be D2 divided by T2. It is again 20 centimeters divided by 41 divided by 240. Okay, so let's then put this information on this second equation. The sum of the girl's momentum and the boy's momentum should be add up to 0. Okay, as I said, since the girl is moving toward the left, let me bring this over here. The girl is moving toward left, we will take this as minus, okay? And the boy is moving toward right, this is plus. So the sum m1 v1 prime plus m2 v2 prime must be equal to 0. And what we want to find is m2. We want to find boy's mass. By this, m2 is going to be m1 v1 prime minus divided by v2 prime. But v1 prime is itself negative, and the 20s are both for both is the same. Okay, m1 multiplied by the division of v1 prime to v2 prime, it is going to be 41 divided by 37. Okay, you can just verify this by putting all this over here. v1 prime, and these 20s will cancel out, these 240s will cancel out, but v2 prime is proportional to 41, but the v2 prime is denominator over here, so it's going to be 41 divided by 37. So obviously from even that information, from this information, you will notice that the boy's mass is going to be larger than girl's mass because of this fraction. This 41 divided by 37 is larger than 1. Okay, so let's do it anyway. Let's do it over here. I know that m2, I know what m1 is, 79.8 multiplied by 41 divided by 37, and I will just do this on my calculator. Okay, 79.8 0.8 multiplied by 41 and divide this by 37. It is just 88.4 kilograms. Okay. So this is the mass of boy plus the cart, but the cart mass is 22 grams. So mass of boy is going to be 88.4 minus 22. It is going to be 60 6.4, right, kilograms. So you see, we just figured out the boy's mass to be 66.4. The girl's mass is 57.8. The girl's mass is 57.8. Well, girls are lighter than boys most of the time, anyway. So, but it was clear that the girl was moving faster, right? She was moving, taking this 20 centimeters in 37 frames, while the boy was going the same distance in 41 frames. That means boy is a little lighter, smaller velocity in compared to the girl. Okay. So that's it. I mean, just we found the mass of the boy to be 66.4 kilograms just by using the conservation of momentum law. Okay. All right. So that's it. I mean, I'm not going to go further for today, and this is just the initial problem solving, together with explaining what the momentum is, and later in this in forthcoming weeks, I will also explain what the impulse is and what the forces are involved, the interaction forces between the components of the parts systems involved, how to find them also. For example, we will be able to find the average force that both the boy and girl applies to each other. This is another point. You might just wonder what forces that the boy pushes the girl toward left. Also, the girl is pushing the boy toward right, because the boy also moving to the rightward direction. Well, it's going to be the same, because according to Newton's third law, if one object applies a certain force on the other object will apply the same amount of force on the first one, equal in magnitude but opposite in direction. This is the Newton's third law. We will be able to determine also the average force that these two students are applying each other. I will discuss this next week, okay? And we will further solve other problems also in the forthcoming weeks. Okay, that's all for today, and I will stop here, and we will continue the same subject, solving problems on momentum. If you have any questions, you can ask. If don't, I will see you next week.
Sir,
Yes.
I have a question about frictional force. What would happen if there is a frictional force?
Yes. If there is frictional force, then the momentum will not conserve, because that means on your system there is external force, right? And these external forces usually will not add up to zero, because the frictional force on one part of the system is not going to be the same on the other part, because they are interacting with the surface. Surface is external to the system, because surface is not included in the system. And if you have a frictional force, well, in this example we just ignore the friction, because the wheels of the cart has been chosen in such a way that you can just ignore the friction. The wheels are very freely rotating, and they're not skidding on the surface anyway, you can ignore for such a small period of time. You can always ignore the friction. But if the friction is not ignorable, if it's some have high quantity, then the momentum will not conserve in that case, at least for this system. Okay.
Okay.
It is good that you ask this, because we have limitations of using this conservation law. As I said, but I already put this, that this conservation of momentum is only valid for isolated system, and isolated system means there is no external force. But if you include the friction on the system, then it's not going to be an isolated system. There is an external force on your system in that case.
Okay, thanks.
No problem. Any other questions? Okay, I'll see you next week, and bye till next week.